Scientists have just announced the first images, you've probably seen the news, of a black hole. And with us to explain how this was done and what it means is astronomer Carolyn Crawford. So what actually have they imaged, Carolyn, and where did they see this?
Well, just first to stress, it's not actually an image of a black hole. It's the closest we can get. But you're seeing effectively the silhouette of the event horizon around a black hole. So you're sort of more or less sitting in the shadow it casts towards us. So that hole that you see, I mean, if you look at the image, it's this beautiful sort of annulus, bright annulus with a circle a dark circle in the middle. That's not the black hole. That's the shadow of the event horizon.
It looks like a bit of a bagel in the sky, doesn't it? It's a long way away, though, isn't it?
It's 55 million light years away. And it sits right at the centre of a colossal giant elliptical galaxy called M87. And we've already weighed the mass of the black hole as being 6.5 billion times the mass of our sun.
How do you know that?
We know that because a black hole, you can't see it, but you can measure its gravitational effect on matter around it. And in this case, it's been ionized gas and stars in the vicinity. You look at how they're moving. You can work out what gravity they're responding to. You can weigh the black hole. One thing that has come out of this that's nice is those estimates match very nicely the size of the event horizon we see here. So there's a consistent story about the mass within this black hole.
How were the images assembled or prepared?
The images were taken with something called the Event Horizon Telescope, which is where you mock up a radio dish the size of the Earth by linking together 8 widely separated radio telescopes. And the reason you do that is that if you increase the effective diameter of your telescope, you get a very good, what we call angular resolution. That's the ability to see details. And if you increase the size of your radio dish to that of the Earth, well, you can get a resolution that you could detect a grapefruit on the surface of the moon. And that is ideally matched to the event horizon around the supermassive black hole in M87 and also the supermassive black hole at the centre of our galaxy called Sagittarius A star.
Yes, I was interested that they chose to report on the bigger one that was a lot further away, though, than the one in our own galaxy. Do you think they're saving the best till last? Do you think they've got some big reveal up their sleeves?
Well, the nearer one, and nearer, I mean, it's still 26,000 light years away. The thing about Sagittarius A star is 4 million times the mass of our sun. So it's 1,000 times smaller, it's 1,000 times nearer, but it's also much more variable. It changes in brightness on a much faster timescale. So actually correlating all the data from all these 8 different telescopes is a lot harder work. So there will be a big reveal. They're just being more careful and they're taking longer to do it.
And what do you think they will do next then? Because now we can image black holes. Will they just turn their devices on as many black holes as possible?
Well, first of all, there are improvements. I mean, obviously, we're going to look at more supermassive black holes, different ones, but you can improve the algorithms to try and sharpen the images. We can observe at other wavelengths, try and improve the angular resolution, the detail we can see and see fine structure around the black hole. And if we really wanted to be adventurous, we could perhaps increase in the long future the diameter of this potential radio telescope, put a radio dish on the moon, and again get to far more detail and perhaps see changes in real time of how this material is accreting onto the black hole. Almost get a movie of this accretion as it happens.
We've had a whole slew of questions on our forum, nakedscientist.com. This person says, how many kinds of black hole are there? Do they come in different kinds and flavours?
Oh, yes, there are definitely different flavours of black holes. There are 2 kinds that we regularly observe. You have the ones that we call them stellar-sized, but in fact they're probably 10s times the mass of our sun, and they'll go from about 10 solar masses up to about 60 solar masses. And they're the ones that you find like in the spiral arms of galaxies. They come from the death of stars. But then you get the behemoths that live at the centres of galaxies. And these are what we call the supermassive black holes. And these are the ones that can be millions, if not billions times the mass of our sun. Those are the astrophysical black holes we actually observe. People do speculate, I mean, there are predictions that there could be something called primordial black holes that may be formed either during or just after the Big Bang. But we don't observe those yet, and so that's more speculation.
That question came from Mad Atheist on our forum, who also says, how many of these black holes involve a singularity? Do they all have one? Is that an obligatory thing with a black hole?
Yeah, that's what defines it as being a black hole. The singularity is where you have something that goes to infinite value, and we're talking about something that's basically infinite density. So by definition, all black holes are the singularity.
And what happens he is asking, when you get to the event horizon, to the speed of light, does light inside a black hole change speed, or is it still running at the speed of light?
Who knows? Once things goes over the event horizon, our physics break down. We couldn't speculate.
Evan AU, also on the forum, says, what sorts of temperatures did they observe in the accretion disk, the whiter sections and the orange sections in the images from the material that's orbiting the black hole?
Be very clear that this image is an image. They're not measuring temperature. Those different colours are not a temperature scale, it's just intensities. You can't measure temperature from this image. What we can guess is because the observations take place at sub-millimetre wavelengths, we reckon that the particles that are giving off this radiation are relativistic. So that's equivalent to being very high temperature indeed, perhaps, 1 billion degrees or so.
And that is because they're being tugged on so hard by the intense gravity in the area of space they're finding themselves.
Exactly. They're being compressed, there's friction, they're whirling around in this extreme gravitational situation just before they get sucked over the event horizon.
And Evan AU also says, is the pressure and temperature in that accretion disk sufficient to cause nuclear fusion?
Well, obviously, the temperature is incredibly high, but the pressure is not there. It's very, very diffuse. It's an incredibly hot plasma, but the density is probably about equivalent to the air in this room. And the thing to get nuclear fusion going, you don't just need the temperature of, tens of millions of degrees like you get in the centres of stars, but you also need that intense density so that there's enough protons that bang in together to start the nuclear fusion. So you're not going to get nuclear fusion in the accretion disk.
And Evan follows up by saying, why didn't they see jets in this image that's been put into the newspapers, for example? Because you do see those jets being demonstrated in some black hole images, don't you?
Of course. And there's a really strong jet in M87, the black hole at the centre of this image. This was, in fact, the first question many of us asked, because it is such a prominent jet. All we can guess is that the surface brightness of the jet emission is so low in contrast to the stuff around the shadow of this event horizon that it's just not coming up in this image. And you've got to remember, you're looking right down to where the jet is being generated. We don't know how that's done, but it's possible that at that point you're accelerating all these particles to relativistic speeds that explode out in this jet. You haven't got that surface brightness that it would emerge in this image yet.
And where did these jets come from at all?
Well, I wish we knew. There are all kinds of ideas, but they're all linked to the fact that you have a rotating black hole. Now, that's going to tug space around with it, material in that space, which includes magnetized plasma. So it acts like a giant motor. You're twisting, you're distorting the magnetic field. And if that snaps back into a simpler reconfiguration, you're going to release huge amounts of energy, which can spit out these charged particles along the rotation axis of the black hole. And you get these twin jets that stream out into the galaxy beyond.
They're very striking, aren't they? Georgiev wonders, is there any way we can know anything related to the mass distribution inside the black hole, i.e. over the event horizon? This goes back to the point that the person was asking about knowing about the speed of light or not inside the black hole. I guess the answer is going to be no.
The answer is no. The event horizon is literally the horizon beyond which we can see no events, and we can do the thought experiments, but it's completely locked away. Anything that's going on beyond that boundary is completely locked away to us at the minute. There's no way we can work it efficiently mathematically or observationally.
Last question from me. What was your personal reaction when you saw the announcement this week and saw the papers?
I loved it. I mean, if anything, it was first it was, where's the jet? The standard question. And the other thing was just how remarkably similar it looked to all the predictions, all the theoretical models that I've seen many of my colleagues working on. And here it came out looking like a textbook example. Now, in one way, that is really exciting, really rewarding, but also just a tiny bit disappointing.
Carolyn, thanks very much for telling us and sharing your enthusiasm. Carolyn Crawford, she's from the Institute of Astronomy at the University of Cambridge.